Previously, we have discussed the definition of greatest common divisor as well as some of its elementary properties. Yet, in practice, the previous discussion is of little use without knowing the actual value of the greatest common divisor. Sometimes, when the magnitude of a and b are relatively small, it is possible to observe their greatest common divisor by using our eyes, or alternatively, by using methods like brute force. However, as the magnitude of a and b become large, it is in general impossible to determine their greatest common divisor without carrying out any computation. To this end, let us introduce the Euclidean algorithm, which is a well-known algorithm in computing the greatest common divisors for a given a and b. In the rest of today's section, we will first describe the detailed scheme of the algorithm and illustrate it with examples, postponing its validity and efficiency to later sections. From now on, let us assume without loss of generality that both a and b are natural numbers. After all, the greatest common divisor of a and b is equal to that of their absolute values. Thus, if either a or b is negative, we can replace it by its absolute value, thereby returning to the present setting. Alright, now let us look at the detailed scheme of the algorithm. Recall that the greatest common divisor of 0 and 0 is defined to be 0. Hence, we only need to deal with the case that a and b are not both 0. To this end, let us assume that a is a natural number and b is a positive natural number. Since b is positive, we can perform the division algorithm to a and b, where a is the dividend and b is the divisor. This will give us the quotient q as well as the remainder r. Now, let us look at the value of r. There are only two possibilities. Either r vanishes or not. If r is indeed 0, we will report the value of the divisor b, and it is finished. Otherwise, if r is not yet 0, we will update the dividend and the divisor in the following way. We will set the new dividend to be the current divisor and the new divisor to be the current remainder. Notice that since your current remainder r is not yet 0, the new divisor is therefore non-zero. This implies that we can now launch the division algorithm again, which will produce a new quotient as well as a new remainder. We will look at this new remainder again and see if it is equal to 0 or not. If it is equal to 0, we report the current divisor and the algorithm is finished. If r is still not yet 0, we will proceed as before, replacing the dividend by the divisor and the divisor by the remainder, and launch the division algorithm for another time. We will keep going until r vanishes. And once we find out that r vanishes, we will report the current divisor, which is supposed to be the greatest common divisor of a and b. Of course, so far it might still be slightly abstract by merely looking at this flow diagram. So let us illustrate the algorithm using an example. Let's say we want to compute the greatest common divisor of 2024 and 748. Since 748 is non-zero, we take it as a divisor. Division algorithm shows that 2024 is equal to 748 times the quotient 2 plus the remainder 528. Notice that the remainder is non-zero. Thus, we will take the divisor to be the new dividend and the remainder to be the new divisor. We launch the division algorithm again. This gives the quotient 1 and the remainder 220, which is still non-zero. So what we do? We take the current divisor as the new dividend and the current remainder as the new divisor. And let's do division algorithm for another time. This time we have the quotient 2 and the remainder 88, which is still not 0. So we will take the divisor as the new dividend and the remainder as the new divisor. Now, another time division algorithm shows that the new quotient is 2 and the new remainder is 44. And the remainder is still non-zero. No worries, just be slightly patient. So take the divisor as the new dividend and the remainder as the new divisor. Another division algorithm produces the quotient 2 and the remainder 0. Well, that is great. So now the remainder is indeed 0. What we do, we conclude that 44 is the desired greatest common divisor for the original pair 20, 24, and 7, 48. Alright, now you have seen what is the Euclidean algorithm and how it works. In the coming section, we will discuss why it works.